Hello students, today I am here to discuss one of the important topics of the subject of industrial metallurgy or physical metallurgy with you, and this topic is called heat treatment. In this particular lecture, we will try to introduce to you the basic concept of heat treatment or the heat treatment processes. This is the table of contents that we will cover in this lecture. What is the need of heat treatment processes? Then we'll try to see that why steels are still industrially most relevant materials, why they are commercially most used alloys. We'll also cover and we'll try to explain what are exactly heat treatment processes and what's the working principle behind their working or behind their success. So let's start. Students, just think that the area of application of any material, any metal, any alloy system, that is very confined. And why is it confined? Because the mechanical properties of a material system are limited. Every material system has got some specific properties, and because of those specific properties, it has some specific domain of applications. But what if you decide that I should be able to use the same material for a wide range of applications? So this exactly is what we do in physical metallurgy or industrial metallurgy, that we try to have control over the mechanical properties of a material. Means the same material, under some conditions, it would have some specific mechanical properties, but the same material, after it has received some processing, can show you some another set of mechanical properties, and then under different conditions of having different mechanical properties, its areas of application can be increased, right? So suppose a same material at one point in time, because of a certain processing and composition that it has, it is very soft and ductile. So it is being used to draw wires. But at the same time, after receiving some another processing, the same material has become very hard. So now you can make knives or you can make tools out of it. So this field of engineering, where you try to develop control over the mechanical properties of a material, you try to learn as to how I can change the mechanical properties of a material system to my advantage, to suit or to make that material fit into different type of applications. That is the role, that is the scope, that is the main area of application of industrial metallurgy or physical metallurgy. So in physical metallurgy, we change the mechanical properties of a material system through three routes. One of the routes is that we change the chemical composition of a material system, and when we change the chemical composition of a material system, we term that processing route as alloying, right? But another method is that you apply some pressure or force onto a material, like forging, like rolling. Now, the main application of mechanical treatment is that we wish to bring the material to a particular shape and size. But in the process, when we are applying that force or when we are applying that pressure to bring the material into a certain shape or size, the mechanical properties also get changed. And the third and the final route in industrial metallurgy or physical metallurgy, how we change the mechanical properties of a material system, is through these set of processes which are called heat treatment, which is the topic of discussion in this lecture. So what did I say? I said that in physical metallurgy or industrial metallurgy, the prime objective is to change the mechanical properties of a material system according to a specific application which you have in mind. And there are three ways how in physical or industrial metallurgy we change the mechanical properties. One is by alloying, second is by giving some mechanical treatment, and third is what is our topic of discussion, by giving a suitable heat treatment to your material system. Now, before I start with the explanation as to what are heat treatment processes, let's again see as to why steels are commercially so successful, why they are still the most extensively used alloys in the industry. Students, there are some reasons for it. See, number one, steels can be produced in bulk quantity, and that too very economically. So their production is very economical. Second, the response of steels to major manufacturing processes, whether it is welding, whether it is forging, whether it is cold rolling, whether it is hot rolling, whether it is any type of machining, the response of steels to the main manufacturing processes is very, very good. So that also makes steels presence everywhere in the industry. Another important reason is that steel's properties can be altered, they can be modified, they can be improved by a process called alloying. Though this is expensive, but yes, see, stainless steels is a very classic example. You have plain carbon steels, you put some 10.5% or 11 weight percentage of carbon in it, they become stainless steel, which are totally anti-rusting, anti-corrosive, right? And you can improve upon the mechanical properties of the steels by a process called alloying. But as I said, this process is little costly, so it makes it sometimes very forbidding. But there is another route that is available. The properties of the steels can also be modified, improved, varied by these set of processes which are called heat treatment. Now, the beauty about steels is that they respond to every type of heat treatment that is known. We have some heat treatment processes like we have annealing, we have normalizing, we have hardening, we have tempering. The good thing about steels is to every heat treatment, they will respond positively. Means every heat treatment is meant to fulfill some purpose. Steels are a category of alloys which would respond to every heat treatment. Like aluminium. Aluminium responds to a heat treatment process called hardening. It responds very well to this heat treatment process called hardening. But to other processes like annealing or normalizing, no, aluminium would not respond. Means they would not be able to bring about a change in the aluminium alloys through other treatments. But steel, whether it is annealing heat treatment, whether it is normalizing heat treatment, whether it is hardening heat treatment, whether it is tempering heat treatment, steel will respond to every heat treatment and will modify its properties accordingly. So this is why steels are so important. All these reasons make steels that important. Then students, what is meant by this term, or what is the scope of these processes which are called heat treatment processes? So as I named some of the heat treatment processes, one of the heat treatment processes, as I said, is called annealing. Then there is another heat treatment process, very important one, which is called normalizing. We have another heat treatment which is called hardening. We have another heat treatment process which is called tempering. Like this process is called annealing, but annealing further is of many, many types. We have full annealing, we have spheroidization annealing, we have black box annealing, we have diffusion annealing, we have isothermal annealing. Means processes are many. And every heat treatment process, the basic function is to improve upon the mechanical properties of a given steel. Yes, those properties may be different. Like annealing is always to induce softness in a steel. Normalizing is always to increase the strength of the steel. Hardening is always to increase the hardness of the steel. But whatever heat treatment process it is, it has got three common steps: heating, holding, cooling. So whether you are giving annealing or normalizing or hardening, you are always going to follow these three steps. Heating, which is also called austenization in most of the cases, not all, but most of the cases, we'll discuss more on it. Then there is this step called holding, where you hold at the heat treatment temperature. This is also called soaking. And finally, there is you do slow cooling or fast cooling. So you follow a particular cooling route. This is the last step in heat treatment. So I've depicted it over here, that in any heat treatment process, the first step would be from room temperature at a specific heating rate. You will heat the steel to this temperature. called the heat treatment temperature. In case of annealing, it would be called the annealing temperature. In case of normalizing, this would be called the normalizing temperature. But commonly, this would be called the heat treatment temperature. Once you have taken your steel component to the heat treatment temperature, now you will hold or soak the steel at that temperature for some period of time. And finally, having done this at a particular cooling rate, which is most important step, you will cool down your steel till the room temperature. And following these three simple steps, students, heating, holding, cooling, you will be able to transform the mechanical properties of your steel component completely. But how does that happen? We'll see it in the next slide. But why heat treatment is not a single process. It's a common name given to several processes. Every process, every heat treatment process might have a different function to be performed, different mechanical properties to be induced in the steel component to which they are being given. But then why they have been clubbed and put into this single basket called heat treatment? Because they follow the same steps: heating, holding, cooling, austenization, soaking, cooling. So that's the reason. So this definition that you see here on the board is given by American Society for Testing of Materials. They say heat treatment is defined as a combination of heating and cooling operations timed and applied to a steel component. Essentially, the steel component should remain in the solid state. So during heat treatment, you will never see that liquid phase appears in the steel. So steel would be heated from the room temperature. It would be held, it would be cooled, but nowhere would the liquid phase appear in the steel. So steel will always remain below its solidus temperature. So heat treatment is a combination of heating and cooling operations timed and applied to a steel component in the solid state to bring about changes in the phase. Changes in the phase that were earlier there, because whatever phases were earlier in the steel, right, students, they have to be changed. Then only the mechanical properties would change to obtain. And why are we doing all this? Because we were not happy with the mechanical properties which the metal or the alloy system was showing. We wanted to change this mechanical properties. We have not adopted the route of alloying because it might be costly. So if we are following the route of heat treatment, we are simply heating and then cooling the steel at a given heating rate for a given holding time at a given cooling route. Very slow cooling routes can be followed. Very, very fast cooling routes will be followed. This is over temperature versus time. And why are we doing these heating and cooling operations? Just to bring about a change in the microstructure, just to bring about a change in the grain size, the phases that would be seen in the steel under room temperature conditions. And then because you have changed the microstructure through heat treatment, the mechanical properties would also change. Same with alloying also. Why does after alloying properties change? Because the microstructure changes, right? So I'll talk more about it in the last slide, that what is the principle behind the heat treatment processes. You see, right in the beginning lectures of industrial metallurgy or physical metallurgy, we keep on saying that any alloy or any metal system, so any metal or any alloy system, whatever mechanical properties it is showing some value of hardness, it is showing some value of strength, it is showing you some value of ductility, impact strength, fatigue resistance, creep resistance, whatever it may be. Any metal or an alloy system under any conditions. And what do conditions mean? It would be at some temperature, the material system would be of some composition, the material system would be subjected to some pressure. Pressure generally is atmospheric pressure until and unless some specialized things are being done. So whenever any metal or an alloy system is present under some conditions of temperature, composition and pressure, it is showing you some mechanical properties. But why is it giving you those mechanical properties under those conditions? Because under those conditions of temperature and pressure and composition, your metal or alloy system contains some particular microstructure in it. So under some given conditions where mechanical properties are being investigated, mechanical properties are being given of some specific value because the materials system, alloy or the pure metal, has got some peculiar microstructure hidden in it under those conditions of temperature, pressure, composition. So microstructure mainly consists of, there would be some grain size of the phases that are present, and that there would be some phases present which we call as phase details. Some number of phases would be present, they would be of some specific type, they would be having some volume fraction, they would be having some shape, size, distribution. That all makes phase details. And each phase would have some grain size. These two things make up the microstructure. Microstructure makes up the mechanical properties of the alloy under some given conditions. So if you are happy with the microstructure, if you are happy with the mechanical properties which an alloy system is showing, you are happy with the microstructure it is containing. If you are not happy with the mechanical properties a material system is showing to you under some given conditions of temperature, pressure, composition, you are in reality not happy with the type of microstructure that it is containing. So if you have to change the mechanical properties which a material system is showing, you have to change its microstructure. And in steels, students, this microstructure comes from high temperature phases decomposition. That high temperature phase is called austenite. So when in any steel, when that steel was under high temperature conditions, a phase called austenite was present. And when you start cooling the steel, depending upon what type of cooling conditions are being given to the steel, very slow cooling, intermediate cooling, very fast cooling, that different way of cooling would change the way austenite would decompose or transform. So where is the microstructure coming from? Microstructure is coming from decomposition of austenite, or what we call in metallurgy, transformation of austenite. Now, when you were bringing the steel from a high temperature, when it was containing austenite, to the room temperature, depending upon how steel is being brought to the room temperature, very slow cooling or faster cooling or still faster cooling or quenching, very, very fast cooling, austenite will transform, students, into different phases. For example, if you have a austenite containing steel at a high temperature and you do equilibrium cooling or slow cooling of that steel, austenite present in the steel will have only one option, and that is to change into perlite phase mixture. But if in the same steel, same austenite, the steel was cooled at a faster rate, might be it will not now change into perlite, but it will change into another phase mixture which is called bainite. And if your steel was at high temperature, it was containing austenite, you didn't do slow cooling so that austenite could have decomposed into perlite, you didn't even do slightly faster cooling so that austenite could have changed into bainite, rather you preferred doing a very, very fast cooling which is called quenching. Austenite will neither change to perlite nor to bainite, but it will change to a very, very hard phase called martensite. So students, when you are bringing the steel containing austenite to room temperature, austenite will transform into different phases depending upon what type of cooling rate is being followed. And finally, what combination of phases are being seen depending upon the cooling route that you followed will decide that what would be the room temperature microstructure of your steel. For example, your room temperature microstructure of the steel could be, sir, it is containing perlite, but there is about 10% martensite also. Because you did very slow cooling for 90% of the route, but for remaining 10% of the route, you suddenly cooled, and that sudden cooling led to martensite. Initial slow cooling led to 90% perlite. So now this is the room temperature microstructure of the steel so what did we say? Initially you have to have austenite in the steel. The heating step that you followed, see, this is how you showed heat treatment. This is temperature, this is time. So you said initially we heat the steel. Why are we heating the steel? To form austenite phase in it. Why are we holding the steel? The austenite that initially gets formed at the heat treatment temperature is not chemically homogeneous. So through this holding, we get the diffusion process get done in the process, and we make this austenite, which was not chemically homogeneous, we make it chemically homogeneous. And finally, austenite, chemically homogeneous austenite is there with you. The third step of heat treatment, whether slow cooling or slightly fast or very fast, whatever type of cooling you follow will decide ultimately at the room temperature what type of phases would be seen. Here you are seeing perlite phase mixture and martensite phase. So the first two steps, heating plus holding, form austenite, and they formulate a particular grain size in the steel. Grain size is formulated during heating and holding. But phase details, what phases would be seen in the microstructure, that is governed by the way you cool the steel. So first step of heat treatment and the second step of heat treatment will freeze this portion of the microstructure. What type of grains are going to come? So if you heat to a very high temperature, maybe very coarse grains would come. If your heat treatment temperature is lower, the grain size would be fine, right? So this is all austenite still. So this austenite that got formed here at the heat treatment temperature is still not chemically homogeneous. So you give this holding. Austenite becomes chemically homogeneous. Now this 100% chemically homogeneous austenite is ready to get transformed into the microstructure you wish to see under room temperature conditions in your steel. So the type of microstructure you wish to see, for example, you wish to see 100% perlite, you will do equilibrium cooling, slow cooling, and here now under room temperature conditions you will only have perlite everywhere. So who has decided the phase details? The type of cooling that you were doing. You do very, very fast cooling, same austenite will change to 100% martensite. Or you do first slow, then fast cooling, you will get a mix of these. So this is the basic principle how heat treatment processes form. Heat treatment processes, no properties are given by microstructure. Who gives the properties? Microstructure. Who gives the microstructure? Transformation of austenite. So what does heat treatment process do? It first forms austenite in the steel, makes it chemically homogeneous, finally cools it and gets the particular phases that you wish to see. And you just have to know what type of microstructure would give what type of mechanical properties. And then you should know what type of processing has to be done during heat treatment to get that microstructure. So like I named a process called annealing. You know, in annealing, you have to make a steel very soft and ductile. That would come through 100% perlitic structure. So bacho, you heat, hold, very slow cooling. It is during equilibrium cooling that austenite transforms to perlite. But now the same steel on a different occasion, you say, no sir, now I wish that this steel no more remains soft and ductile. I want to make it hard. So you pick up not annealing, but now you pick up another process from the heat treatment basket, which is called hardening. Same heating, same holding, but now not slow cooling, rather very fast cooling, which is called quenching. You get 100% martensite. तो आपको कहां से मिली थी सॉफ्टनेस? 100% परलिटिक स्ट्रक्चर से. 100% परलिटिक स्ट्रक्चर कैसे मिला? ऑस्टेनाइट की स्लो कूलिंग करके. लेकिन अब सेम स्टील में अगर आपने परलाइट नहीं चाहिए क्योंकि सॉफ्टनेस नहीं चाहिए, हार्ड चाहिए, यू क्वेंच द स्टील, ऑस्टेनाइट विल ट्रांसफॉर्म टू 100% martensite. So that's the beauty of heat treatment processes. Simple heating and simple cooling. No alloying required. By simply heating and cooling the steel, you can change its microstructure and its mechanical properties, and it's a very, very economical process. बिल्कुल महंगी नहीं है. Steels हर तरह की heat treatment process को respond करती हैं. हीट ट्रीटमेंट प्रोसेस कोई भी आप उठा लो, जो वो हीट ट्रीटमेंट प्रोसेस कर सकती है, स्टील को अगर वो हीट ट्रीटमेंट प्रोसेस दी जाएगी, स्टील्स विल रिस्पॉन्ड एंड चेंज देयर माइक्रोस्ट्रक्चर अकॉर्डिंग टू दैट हीट ट्रीटमेंट प्रोसेस. इसीलिए आप स्टील्स की प्रॉपर्टीज को एक बहुत वाइड स्पेक्ट्रम पर चेंज कर सकते हो. दैट इज व्हाई दे आर कमर्शियली मोस्ट commonly used, most largely used steels in the industry. I hope I have introduced you to the basics of heat treatment, that what are heat treatment processes and how do they really work to bring about the changes in the microstructure of a given steel specimen. Thank you for watching.